What if I told you that the word king minus the word man plus the word woman equals queen? Watch. The direction from man to king, this is the royalty direction. Now copy that exact same arrow starting from woman. It lands on queen. V king minus phi man plus V woman approximately equals V queen. This is not poetry. This is linear algebra. Meaning becomes geometry. And this idea is the foundation of every language model on Earth. Embedding spaces. How did AI learn that king and queen are related? The answer starts with a simple but powerful idea. You shall know a word by the company it keeps. J.R. Firth, 1957. Take a sentence. The cat sat on the mat. Slide a window across it. The center word is sat. The context words are everything within the window. Words that share similar contexts end up with similar meanings. That is the distributional hypothesis. But first, the problem. A one-hot vector has 100,000 dimensions, one for every word in the vocabulary. The word king is a 1 at position 3,000 and zeros everywhere else. In this space, every word is equally distant from every other word. King is just as far from queen as it is from banana. Word2Vec fixes this. It learns a dense vector of just 300 numbers for each word, where distance finally means something. Here is Skip-gram, the architecture behind Word2Vec. Given a center word, predict the context words around it. The input passes through a weight matrix W to produce a 300-dimensional embedding. Then a second matrix W prime produces probabilities over the entire vocabulary. This is softmax, the dot product of the output vector with the input vector, normalized over all words. But there is a problem. The denominator sums over every word in the vocabulary. 100,000 terms for every single training example. That is way too expensive. The solution is negative sampling. Instead of computing probabilities over the entire vocabulary, just focus on a few words. Take the real context word cat and pull it closer to the center word, sat. Then randomly sample a few negative examples, words like quantum, banana, telescope, that probably do not belong in this context, and push them apart. That is it. The computation drops from 100,000 terms to just 5 to 20. The negative words are sampled from a noise distribution, where word frequency is raised to the 3/4 power. This gives rare words slightly more chance of being sampled. Before training, the embedding space is chaos. 30 words scattered randomly across 3 dimensions. Each color represents a category. Green for animals, blue for countries, purple for emotions, orange for food, and gold for royalty. Now watch what happens when training begins. Words that appear in similar contexts are pulled toward each other. Cat and dog share contexts like pet, fur, and walk. France and Japan share contexts like capital, language, and culture. Gradually, structure emerges. Animals cluster together. Countries cluster together. Emotions find each other. The loss drops. The model is learning. And after billions of these small adjustments, meaning has become geometry. Here is what the king-queen analogy actually looks like geometrically. The direction from man to king is the royalty direction. The direction from man to woman is the gender direction. To find the answer, the model computes cosine similarity, the angle between two vectors, normalized to a range from -1 to 1. It searches the entire vocabulary for the word whose vector is closest to king minus man plus woman. But here is the honest truth. First, the exclusion trick. If you do not exclude king, man, and woman from the candidate list, the nearest word is usually king itself, not queen. Most demonstrations do not mention this. Second, cherry picking. On the Google Analogy test set, with 19,500 questions, Skip-gram scores just 55%. On the Balanced BATS dataset, even the best model scores under 30%. Accuracy across categories varies wildly, from 10% to 99%. Third, bias. Word2Vec trained on Google News Maps computer programmer closest to man and homemaker closest to woman. Bolakbasi and colleagues showed the correlation with stereotypes is 0.51. Look at the numbers side by side. Skip-gram 55% on the Google test. Glove does better at 75, but that test is heavily biased toward country capital pairs. On the Balanced BATS benchmark, even Glove drops below 30%. Levy and Goldberg showed that Word2Vec is secretly doing matrix factorization. The dot product of two word vectors approximates the pointwise mutual information minus log k, the same statistics that count-based methods capture. Consider the word bank. I walked along the riverbank. I opened a bank account. Same spelling, completely different meanings. Word2. Vec gives bank one single vector no matter the context. BERT gives it a different vector every time, shaped by the words around it. Let us compare them. Word2. Vec gives every word exactly one vector: static, fixed, frozen. BERT gives the same word a different vector depending on context. The word bank in 1,000 different sentences produces 1,000 different embeddings. How does BERT do this? Self-attention. Each token is projected into 3 vectors: a query asking what am I looking for, a key saying what do I contain, and a value, the actual information. The attention formula computes how much each token should attend to every other token. The dot product of queries and keys divided by square root of dk, then softmax, then multiplied by values. Here's what that looks like. In the sentence, the bank is by the river, the word bank attends most strongly to river with a weight of 0.70. That is how BERT knows this is a river bank, not a financial one. BERT base uses 12 layers, 768 dimensions, 12 attention heads, and 110 million parameters. How contextual are its representations? Ep10 showed that less than 5% of the variance in BERT embeddings can be explained by static embeddings, meaning 95% of the information comes from context. The result? BERT improved the glue benchmark by 7.7 points, achieving state-of-the-art on 11 tasks simultaneously. Context is everything. In the real world, how do we measure similarity between 2 embeddings? Cosine similarity measures the angle between 2 vectors. It ignores magnitude and focuses purely on direction. Euclidean distance, on the other hand, cares about position and magnitude. For text embeddings, cosine is usually the better choice, and when vectors are normalized, cosine and Euclidean give the same ranking. This is why vector databases exist. A user asks, how do I reset my device? Traditional keyword search finds nothing, but semantic search using embeddings finds restoring default settings. Zero keyword overlap, same meaning. To search billions of vectors quickly, algorithms like HNS-W build multi-layer navigation graphs, enabling search in O of log n. This is the foundation of RAG, Retrieval Augmented Generation. Step 1, chunk your documents into pieces. Step 2, convert each chunk into a vector. Step 3, store them in a vector database. Step 4, when a user asks a question, embed the query and retrieve the top k nearest chunks. Step 5, feed those chunks as context to the language model. The result? Grounded answers, less hallucination, no retraining needed, domain-specific knowledge on demand. In 2006, Netflix offered $1 million to anyone who could improve their recommendation system by 10%. 100 million ratings, 480,000 users, 17,770 movies. The ratings form a sparse matrix. Most entries are missing. How do we fill in the blanks? Matrix factorization. Decompose the rating matrix R into 2 smaller matrices, P for users, Q for items. The predicted rating is the global average plus a user bias plus an item bias, plus the dot product of the user and item vectors. Here is the key insight. Users and items now live in the same low-dimensional space. The dot product measures how well their tastes align, and the dimensions learn interpretable factors: serious versus fun, mainstream versus niche. Here's what that space looks like. Users are circles. Movies are diamonds. Alice sits close to comedy A, so we predict she will like it. Bob is near drama B. The closer the dot product, the stronger the recommendation. Spotify uses the exact same idea. Songs are words, playlists are sentences. That is literally Word2Vec applied to music. And Rendell showed in 2020 that a simple dot product, properly tuned, outperforms complex neural networks for similarity. The geometry is powerful enough. Why does any of this work? Why can meaning be captured as geometry? The Manifold Hypothesis. High-dimensional data lies on or near low-dimensional manifolds. Think of Earth's surface. It is a 2-dimensional manifold sitting inside 3-dimensional space. Word2Vec captures the usage patterns of over 100,000 words in just 300 dimensions. The space of meaning is compressible. On a manifold, distance is not a straight line. The Euclidean distance cuts through empty space, but the geodesic distance follows the surface. The true distance between meanings curves along the manifold. This idea goes far beyond words. OpenAI's CLIP maps text and images into the same 512-dimensional space, trained on 400 million image-text pairs. The same embedding principle applies to text, images, music, proteins, code, and graph structures. Dar and colleagues showed that every computation inside a transformer can be understood as a geometric operation in embedding space. Meaning is geometry, all the way down. First, Word2Vec learns meaningful vector representations from the context words appear in. Second, the famous king minus man plus woman equals queen analogy is compelling but limited. Honesty about these limits matters. Third, BERT gives the same word a different vector depending on context, capturing 95% more information than static embeddings. And fourth, the Manifold Hypothesis. Abstract meaning becomes spatial geometry. This is the foundation of every language model. 10 episodes, from vectors and matrices in episode 1 through gradient descent, Bayes' theorem, backpropagation, softmax, universal approximation, loss landscapes, convolution, and SVD, to embedding spaces in episode 10. Each episode builds on the last. Each concept connects to every other. And next time, we will discover the mathematics of predicting the next word, Shannon entropy, cross entropy, perplexity, information theory.